Well, good afternoon. It's 2:33. Actually 3 minutes late getting started for class today, but I'm the only one in the room right now, so I guess I'll go on and get started. Even though I am the only one here, if I can get the current slide to come up. There it goes. Okay. I think I'll wait to make announcements until somebody's in the room to hear them. So we'll pick up where we left off last time. I would ask if there are any questions, but no one's here to ask. So we're in section 2.2, separable equations. We had made it through example 3, and now have an initial value problem, so you don't have to worry about the families of equations. You just have to pick the one that fits the initial condition. So here's our equation, example 4. Solve this. Let me see if I need to get my pen set up. Okay. Solve this. E to the 2y minus y, ugly minus sign, that's in parentheses, times the cosine of x dy dx, there's the derivative, is equal to e to the y sine 2x. Okay? And the initial condition is when x is equal to 0, y of 0 is equal to 0. Okay, lots of zeros there. All right. Now, again, there's probably several ways in the future you'll see that you can solve this, but for right now, the only way we have under our belt is separation of variables. Okay? Well, one thing obvious to do is get the dx to the other side, write it in differential form. But we also want to move the cosine x to the other side. So we'll divide this side by cosine x, and we'll divide this side by cosine x. Okay. Well, we also need to get this e to the y to the other side, so we'll divide this here and this here as well. Now, if you don't mind the sort of pure mathematics viewpoint of not separating these, but what we're doing is really writing it as a differential form, but put the dx on this side. Okay, you can think of that as multiplying both sides by dx. Really isn't what you're doing, but that's what we'll do it. So now the ey's go out here, the cosine x's go out here, the dx went out. We got a problem, Houston. Let's see what it is. Well, first let's look at this. Here we have e to the 2y over e to the y. That would just be e to the y, right? Because y, when you're dividing exponential forms, you subtract the exponents. So 2y minus y is y. So we'll just leave it like that. But if we did that way, then that leaves us minus y over e to the y. Okay, that looks like it might be a problem in the future, but we'll see. Okay, and this is all times dy. And on the right-hand side, hey, I don't like having two different arguments of trig functions. So what we need to do is come up with what is sine of 2x? Well, from your double angle formula, we know that sine of 2x is 2 times the sine of x cosine of x. And that's divided by cosine x, which now the cosine x's go out. So it's just 2 sine x dx with the same initial condition, y of 0 is equal to 0. X equals 0, y is equal to 0. Okay, I'm going to pause for just a moment here. I've got to talk with Dr. Bryant for a minute. Wait, wrong pause. All right, sorry about the pause there. Dr. Brandt had just gotten in, and I needed to get some data from him for that I'll need Friday at a meeting that I'm going to be at, and he won't be on campus tomorrow. And I've got to, as soon as this class is over, I've got to book it to the Birmingham East Campus to teach a physics class. So it was catch them then, or I might miss them. All right. Now I was just saying. Oh yeah, we had just done this. So now we have our variable separated. We have it simplified as much as I think we can. So now we integrate both sides of the equation. All right. Now, I know what the antiderivative of e to the y is. That is e to the y. But this one is a different issue. Now, you might choose to write that minus the integral of y e to the minus y dy. I don't know if that makes it any better or not, but I think this one we have to do integration by parts. That's my gut feeling on it, is what's going to work. So let's let u equal y and dv equal e to the minus y dy. Then du is equal to dy, and v would be minus e to the minus y dy. Oops, not dy. You don't have a dy on the other. Let's make sure that works. You take the derivative of v, making dv up there. Derivative of minus e to the minus y would be minus e to the minus y times a minus 1, which would be e to the y, so e to the minus y. So I think that is correct. Okay? And then integration by parts says you take this part, and there's a minus with this, so this will be e to the y from what you had here, minus a minus, which is plus y e to the minus y, okay? And it would have been a minus. Now you had a minus there, and then a minus for your derivative, your integral, because your integration by parts is uv minus dvu, integral of dvu, v du. So that would make that a plus, but then you got a minus in there, so it's another minus, I believe. Minus signs really will trip you up badly. And then it's the bottom line here. I put the minus sign out front, so that would be the antiderivative of e to the minus y dy. Okay, from here. And that's equal to antiderivative of 2 sine x. Just pull the 2 on the outside. Antiderivative of sine x is a minus cosine x. Okay, and there's that one done. Well, we got one more little integral to do here. So that'd be e to the y plus y e to the minus y. And then when you do the antiderivative of e to the minus y, that is minus e to the minus y. So that minus makes that plus, so it's e to the minus y. And that's equal to minus 2 cosine x plus c. Normally, okay, that's indefinite integral. But we have initial value problem. When x equals 0, y is equal to 0. When this y is 0, this is a 1. When this y is 0, the whole thing goes to 0. When this y is 0, you have another 1, so you got 2 on this side, and on this side you got a minus 2 times cosine of 0 is 1 plus c. Okay? Well, this is 2. Add 2 to the other side, c is equal to 4. Okay? And in your text, they show a family of curves there. In the first figure 2.2.2, which is your g of xy, which is e to the y plus y e to the minus y plus e to the minus y is equal to, or plus cosine 2x. There's that function, which is, you know, what we set equal to 0. It would be 0 if you added 2x to both sides. Okay, that's the family of curves. Okay? When c is equal to 4, you get that blue curve there, the one that goes through the origin. Okay? So that's the one. Now, why they show the level curve at c is equal to 4, I'm not sure, just to show you a different one, but that obviously doesn't go through 0. Okay? So that's your solution. Now, c is equal to 4, so then to write the answer, you don't leave it like this. You say e to the y plus y e to the minus y plus e to the minus y. Sorry about that. Is equal to, let's plug in the 4 minus, so aggravating, minus 2 cosine x. Okay? I don't know why the 2 didn't write completely, but there it is. Okay, there is your solution for this boundary value problem, which does have a one fixed value, and that is the curve that describes that. Okay. Now, you can think of this and see what's happening. Your x, I don't know if doing too much analysis is going to do any good. When y is increasing, then e to the y is going to take over. When y is, let me see if that's right, yeah. When y is decreasing, in other words, getting very, very negative, then e to the minus y's take over. Okay. Now, this is showing this curve is awfully symmetric, as if it's an even function. And it just doesn't look like it's that symmetric to me. It should be. But I may be wrong in thinking about it. I don't know. But anyway, no reason to do much else. They do have a little blurb here on use of computers, and it refers back to the remark section at the end of 1.1, mentioning that it may be difficult to use an implicit solution to find an explicit solution, y is equal to phi of x, and this is one of those type of examples. There's just no way you could get this one to be y as an explicit solution of x, I don't think. Well, maybe so. No. Yeah, I don't think this one does. Yeah, it says sometimes it simply cannot be done. Explicit solutions such as 8, which we just did, are somewhat frustrating. Neither the graph of the equation nor any interval over which is a solution satisfying y is equal to y0 equals 0 is apparent, the problem of seeing when an implicit solution looks like it can be overcome. No, that's just talking. Okay. It does say if an initial condition leads to a particular solution by yielding a specific value of the parameter C in a family of solutions for first-order differential equation, there is a natural inclination for most students and instructors to relax and be content. However, a solution of an initial value problem might not be unique. Okay? And they show this example here, dy dx is equal to x y to the 1/2, where y is equal to 0, has two solutions that fit the boundary condition y of 0 equals 0. At least two solutions. So let's actually go back and solve that one. That's what they're suggesting, and that's what I think they're doing. So let's go back and do that one. Here was the differential equation. dy dx is equal to xy to the 1/2. Now before we just said, they say, hey, here's the solution, verify it is blah, blah, blah. This time we're actually going to find the solution ourselves. Okay? Now this is an initial value problem at y of 0 is equal to 0. Okay. So let's actually do this one. Again, write it in differential form, moving the dx over here to the right-hand side. But that means we're going to divide by the y to the 1/2. So what we have left is y to the minus 1/2 dy, when you divide by y to the 1/2, is equal to the x we left there, x dx. Okay, subject to the initial value of y of 0 equals 0. Sorry, I've got the yawnies now. Before my last class, I was in my office trying to get ready for it, and I just had an enormous sneezing fit. I mean, just one after another after another. Actually, a student came in and said, are you okay? I said, yeah, I just get these every now and then. And ever since then, my head has been so clogged up I can't breathe well. And I think that's just, I have to stop and take really deep breaths just to get some air. All right, at this point, we'll integrate both sides of the equation. Okay? Now, this is just a power function, so this is going to be y to the 1/2 divided by 1/2, which is multiplied by 2. That's equal to x squared over 2 plus c. All right? Now, I think that we could probably multiply or divide everything. Let's see, which way do we want it? Yeah, let's multiply everything by 2. Nah, divide everything by 2. So don't do the plus c yet. Have it y to the 1/2 is equal to 1/4 x squared. Then we'll put our plus c in there. Constant, just a constant, and you can either multiply by 4, divide by 2, whatever you want to do. It remains a constant. So wait till you do all that kind of stuff and go with it. All right. Now, if you were to square both sides of this equation, you get y is equal to 1/4 x squared plus c squared. Okay? Now, given an x, any old x, you can get a y. So let's plug in x equals 0 and see what we get. We're supposed to get y is equal to 0. So 0 is equal to 0 plus c squared. squared, so c obviously is 0. Okay, so that's the curve we use. Okay, now by squaring both sides, it's always a dangerous thing to do. Okay, the reason is you may introduce some extraneous roots. Okay, now from this line right here, but also actually from this line right here, you know that's our original problem. That's the square root of y. Y has to be greater than or equal to 0. That's something I usually like to do at the very first step when I see the problem first written down. Notice if there's anything that is unusual or required to happen. And this, you have to have that because you can't take the square root of a negative number, not in the real number system. So we're going to live in the real number system, so we're going to want that to be greater than or equal to 0, the y value. Okay? Now, they've introduced a quantity a here that I haven't found yet, so I'm going to take a moment looking for it. Well, but the y being greater than or equal to 0 really doesn't add anything here because this describes a parabola, and the parabola, and of course, if c equals 0, it is always, y is always positive, as you see from here, so that's not an issue. Okay, I thought maybe that could be a clue to it, but it really isn't. They introduce another parameter a, and they really don't say where they got it. So rather than doing anything else with it, let's just leave that alone. Okay. I was looking at x less than a certain value, and that's not an issue here. It's the y was, but yeah. Okay. It has many solutions. We'll just leave it like that, and let's just move on. There's not much point. They say they just pull this a out of the air, and it's true. Everything's true about it. But this would be just a solution. Certainly, y is equal to okay. A little bit of what they've done is this. if c is equal to 0, then this would be 1/4 x squared, and that would be 1/16 x to the 4th. Okay. Well, and that certainly is a solution. I said 1/16. One didn't write. Okay, 1/16 x to the 4th. But then they throw in an x squared minus a squared to the squared, and when x is greater than a, that works, and when it's less than a, it doesn't work. No, when it's less than a, you have y, the function is a 0 function. So I don't know. I can't see what their point is here, and nor how they got the a. And they're just saying there's infinite number of solutions here, depending on the a. So let's move on. Sorry, that wasn't. Thought it was going to produce something worthwhile. I don't see it does. All right, here we're going to talk about an integral defined function. And again, going back to remarks at the end of section 1.1, and the second remark there is pointed out a solution method of a certain differential equation may lead to an integral defined function. And here's Dan. Thank you for being here. I get so sick of talking to myself. Just been having a big argument, and I was losing.
Oh, that's terrible.
Yeah. All right, let me turn on the projector and also the light. The light wasn't necessarily very well at sunlight coming in, but just inconsistent. The others are coming today. Muhammad sometimes comes in a little after you two, so he may be here. Okay. I had done example 4, and then the example they had with the top of page 51 that wasn't really an example. It was a rehash of something we had done earlier. Just had to erase that, and now we were talking about the integral defined function on kind of the bottom half of page 51. Going back, they have these remarks at the end of most sections, and they really get into some deep and strange areas, fairly esoteric, you know, not really, well, maybe having meaning later or something, but usually beyond what the sections talked about. So now we're going back and talking about this, and one of these was an integral defined function, and they say that it's pointed out that a solution method for a certain kind of differential equation may lead to an integral defined function. That is especially true for separable differential equations, because integration is the method of solution. And so here was, I don't know if this doesn't look like this is saying a lot. It's sort of a generic thing. dy dx is equal to some g of x. Okay. Given the initial condition y of x0 is equal to y sub 0. Okay. Now, all they're getting at here is there's no y dependence on the right-hand side. There's no y dependence anywhere except dy dx. I mean, that's not really y dependence. That just says the derivative depends on x and x alone. Okay, now especially if they don't tell you what that function g is, you don't know if it's integrable or not. So for something like this, basically what we do is write it in differential form. Dy is equal to g of x dx. Okay, integrate both sides, and this will give you y plus or minus c, but you don't have to do anything with that until you You can combine c's on both sides. And this you just have to leave as the integral of g of x dx, okay, plus some constant c. But you have the initial condition, and this is y of any x, so that y of x sub 0 then would be the integral, okay, and what integral would that be except, and this is going back to fundamental theorem of calculus part 2, I think, if you remember that. It would be x sub 0 to x of g of t dt. Now, that's always seemed bizarre to me, okay? But you see, for this to be a function of x, we have to have x in the problem and not here. So you just use a dummy variable here and get that. And then equal to c, I mean plus c, okay? Well, when you, I'm sorry. When x is equal to x0, and this probably shouldn't be an x0 right here, okay? Not yet, okay? Y of x is equal to that. You're just doing this. Okay, now, when x is equal to x0, this integral goes to 0 because you're going integrating from x0 to x0, okay? So that means your y of x0, which we know from up here is equal to y of 0, is your c, okay? So then we go and plug it back in here, so y of x, it feels like you're running around in circles, but you really kind of are not. And now they put this y0 in front rather than at the end, and it doesn't matter where, but in the book they did this. It's equal to y0 plus this integral from x0 to x, g of t dt. Okay. And that's your solution, okay? And that says almost nothing to me, okay? Except that if that g is then an integrable function, you can come up with a solution, but then that y of 0 will just be added to it because when x is equal to x of 0, that is the only place this guarantees to go to 0, and then you have your y0. And I don't even know why they brought it up here, except saying sometimes you may have those that you can't integrate, so just leave it in integral form. Hopefully you won't run into many of those, but I have a feeling we are right now. Okay, so let's take a look at example 5. Here's the differential equation, dy dx, there's your derivative, is equal to e to the minus x squared. Almost guarantee you this is going to be something you can't do, where y of 3 is equal to 5. So when x equals 3, y is equal to 5. Okay? Now this function, this g of x here, you think of it that way, is a continuous function everywhere. Okay? Absolutely everywhere. If you want to picture a graph of it, when x equals 0, of course, that's equal to 1. And when x is anything greater than 0, then you're doing e to the minus x squared. Okay? Well, x squared is, when x is positive, that's going to be positive. But your integral, that's going to be going to 0 because the minus sign is out front. X squared is always positive, and e to a very large number, negative large number, is going to 0. Okay? Your exponential function, when x is negative, is approaching 0. Okay? X is positive, or your argument is positive, it's getting out of hand. Okay? But even if x is negative, when you square it, it's a positive number, getting bigger as x gets bigger, and you'd still do it e to the minus x, so it's going to be something like this. So it starts at 1 and drops off and goes down this way. All right. If you think of that fairly rigorously, you'll see that's sort of like your bell curve. In fact, that is exactly the form of the bell curve. Okay? The trouble is the coefficient isn't quite right, but it's still that is exactly what your bell curve looks like. Okay? So, it's continuous everywhere, but its antiderivative is not an elementary function. You can't say what is the antiderivative of that. So, I mean, what you would do is say dy is equal to e to the minus x squared dx. And you try to integrate both sides. You can't do it. This will give you y. I'll put the plus c over here this time, is equal to this thing. Well, you can't integrate that. If you had an x dx in there, yeah, you could. If you had, but there's no way. There's no way to integrate that. Even in the tables, they don't give you a way. No elementary function to do that. So this is an integrable solution. So what we have is the integral from of e to the minus x squared dx. And that's all we can do to it. Now, what we're going to do based on the last problem is write this as your x sub 0 to x, change these to t's. Okay? Remember when we did that. Okay. So now we'll have y plus c is equal to the integral of x sub 0 to x e to the minus t squared dt. Okay, again, you can't integrate it, but you can evaluate it when x is equal to 3. So this will be y is equal to, or y plus c is equal to the integral of 3 to x, no, I'm sorry, this x sub 0 was 3. So if you're evaluating at 3, it'll be 3 to 3, which is 0, okay? So that makes this c over here 5. So y plus 5, y minus 5, because this is 0, and that would have to be 0. I mean, when y is 5, y plus c, for this to be 0, c has to be minus 5, because x is 3, y is 5. So when this is 0, y has to be 0. Okay? I mean, y minus 5 has to be 0, so that means y will equal 5. Well, that y is 5, so your c would have to be minus 5. I can't say it right, but that's what it is. Okay, so then your solution, this is minus e to the minus t squared dt. Okay, your solution then would be y minus 5, or the way they write it is y is equal to 5 plus the integral of 3 to x of e to the minus x squared t squared dt. I'm sorry, I always want to put x in there. Okay, but there is the x dependence. Now, for any given value of t of x, 3 you know what it is, that's going to be 5, you can see that. But any other value of x, you can do a numerical integration and approximate it. And that's what all your statistical tables that are based on the bell curve, you know, normal distribution. That's exactly how they got those. Those are numerical integration. Because you can't solve it analytically, so you have to do it this way. But that would enable you to have a process to do that. And somehow it doesn't seem very satisfying, but this is and I move the x to the 5 to the other side, but then this is y of any value x is equal to 5 plus the integral from 3 to x of e to the minus t squared. Let's see if I can clean that up a little bit. It doesn't seem like much of a solution, but it's the only one you got, okay? But again, you can do a numerical, any value x you want to put in there, you can do a numerical solution to it, and you can get values for y. Pick an x, calculate a y numerically, because you can't do it analytically. Okay, and that's the only way you can express your answer. Okay. That finishes 2.2. Homework exercises. Do any of the odds that are in the back of the book, 1 through 21. Any of the odds that are in the back of the book, 23 to 27. Do 29 if it's in the back. And then do any of the odds 31 or 33 if they're in the back. I don't know if 35 is in the back or not, but you could give a shot if it is. Okay. It looks like the 37 seems to be referring back to problem 21. Whether they have an answer there or not, I don't know. But so you can do those if you choose. 37's a lot like that. I have a feeling, well, maybe if they're in the back, you can try them. Okay. Then 39 or 41, initial value problems, you can try one of those if you'd like. They should be in the back. If they are, do them. If not, you don't need to mess with them. 43 is going back to an autonomous type of equation, so you can take a look at that one if you like. 45 to 49, any of those whose answers are in the back, you can try to do those. Now, pretty sure that nothing beyond 51 will be back there because those are discussion type problems. Okay. My head hurts. Or it doesn't really hurt. I'm just can't breathe. It may have been before you came in I said this. In between my first two classes, I had eaten lunch or was in the process of finishing lunch and just went into a sneezing fit. And after that, everything in my head was just so clogged up. I was just fine all morning until then. And now I feel like I'm in a cloud. My voice is all choked up and everything else. So let's get rid of this one and go to another type of equations that we can do. We have ways of solving. This one is not nearly as straightforward as separable. Separable, if you can do it, go for it. This is called linear equations. Okay? And here's the definition of a linear equation. Definition 2.3.1. A first order what does that mean? Differential equation of the form, it's a pretty ugly form, okay? Here, a sub 1 x dy dx D, that's pretty ugly, plus a sub 0 x times y is equal to some g of x. Okay. Now, this is just trying to be as generic as it can be. So any old function of x multiplied by your derivative, y with respect to x, plus any other old function of x multiplied by y is equal to some function of x, some old function of x. Okay, that's why they have the a0 and a1. They remind you of the coefficients of a polynomial. That's not important. That's not what they're there for. It's just two different functions, both a function of x. Okay. Now, this is a first-order differential equation because it only has one derivative. The derivative in it is a first-order derivative, first derivative. Okay. So that's a first-order differential equation. Okay. Now, the key here is there's no y here, only functions of x. If there was y here, this would not be a linear function. Remember, linear differential equation? You can't mix your y's and your y primes, or square your y's or your y prime, or raise them to any power. They all have to be first power. So that's why it says this is a function of x alone times y. You can't have the derivative of y in here. You can't have y squared, or y to the 1/2, or y to the 2/3, or anything else. It only has to be y to the first power. That's why they call it linear. Okay? And the g of x can't have any y's over there either. Your only term with first derivative is here, only x coefficients. The zeroth derivative, in other words, y function itself there, with only x coefficients. And then on the right-hand side, only functions of x. That's what makes it said to be a linear equation in the variable y. Variable y, okay? Linear in y because your y is only to the first power, your dy dx is to the first power, and no cross terms, okay? And this is first order, so we don't go any higher than dy dx. So that's a linear equation in the variable y, okay? That's not your standard form, though, okay? Dream on. If you were to divide both sides of these equations by a1 of x, okay, then this goes to 1. So now we have an equation that looks like this, dy dx plus this is some function of x. Maybe a rational function now. It may be whatever it is. So this, we're going to give a new name, p of x. We didn't like the a's either way, so we named it p. Okay, sorry. Okay. Times y is equal to, and we didn't really like g of x, but when you divide g of x by a1 of x, you still have a function of x. Let's call that f of x. Okay. Now that's a lot better, isn't it? Not really, but I mean... It fits. Now, this is your standard form for a linear equation. That is a linear equation in the variable y, but if you divide by the a1 of x and get this as a coefficient of 1, some p of x there is just some function. Don't assume that's a polynomial function. It's not. I don't know why they use capital P, except they just tradition call it that. The f of x could be anything. There just can't be any y's in it. No y's in the p's, and certainly no y's here. Okay, so that's your standard form. Okay, we're going to seek a solution for that form for which both the coefficient function p and the coefficient function x and the constant function, not constant, the function on the right-hand side f are continuous. Okay, on some interval I, for which both the coefficient functions p and f are continuous. Now, I would call alpha coefficient function, but they do this. All right. They're going to give a couple of examples here, and let's see if they are or are not linear functions. dy dx plus 2xy is equal to 0. Is that a linear function?
Yep.
Yes, it is, okay? In our standard form. One coefficient here, that's fine. 2x is your p of x here, really simple, okay? And your f of x can be 0. No problem with that, okay? How about this one? dy dx is equal to y plus, is equal to y plus 5. Is that a linear differential equation in x?
You can make it.
Yeah, you can. Just subtract y from both sides and you got it. So dy dx minus y is equal to 5. Perfectly fine. The p of x is just a number -1. Okay? Constant function -1. No x is in it. And the f of x is just simply the number 5. Constant function 5. So yeah, that's fine. Okay? Now, while we're on to that, this thing, we could subtract 2xy from this side here, put it over here, divide both sides by y, sort of multiply by dx. You got it separable too. So why even mess with the linear function if it's already separable? Okay, this one, rather than doing this to get it into a linear form, just divide this by y plus 5 and multiply by dx. And that's separable. Don't even mess with what we're going to do later. Much easier to solve it separable. Okay. Much easier. Okay. But how about this one? dy dx plus y is equal to x. Is that a linear function in x? Linear function?
Yes.
Yes, it is. Okay, linear differential equation. Absolutely. But, can you separate that one? No, because the x's and y's are added, not multiplied. See, here, they're multiplied. Here, there's only y, so you can divide. Here, there's the x plus y. Ain't no way to do that. If temptation, which would be close, say, well, let's just multiply everything by dx. No, then you have a y plus y dx plus x dx is equal to x dx. No, that won't work with respect to that. You can't separate the y out from the x. Okay? Can't do it. It's separated by equal sign, but you can't separate them by multiplication or division. Can't do it. So that one we will have to use what we're going to develop now. So if you can separate, separate. They're so much easier to do that way. If you can't, then you turn to the linear functions, which we're about to do. Now, when they start this method of solution, it hinges on a remarkable fact that the left-hand side of the equation can be recast into the form of an exact derivative of a product by multiplying both sides by a special function, mu of x. Okay. All that being said, they're going to come up with some new function, mu of x, multiply everything on both sides by that, and then we'll make it a perfect derivative on one side, and then you can integrate that on the other side. Okay? So, what we're going to do is go back to this form right here. Now this gets, to me, pretty hairy, because they keep putting all sorts of things in there. At the end, it's pretty simple. But to get there can be pretty confusing, I think. And maybe it's the way they do it. I don't know, but it's, so let's clean the slate here. And let's start with, okay, I'll write down what we had before. Your generic form, dy dx, your most general form for a linear equation, dy dx plus p of x, y is equal to some f of x. There's your, that's the standard form. If you can't separate the variables, get it into that form. Okay, first step. Okay, now they're going to multiply everything on both sides by this strange little special function mu of x. Okay, we don't know what it is, but we're going to get there. So now we'll have a mu of x dy dx plus p of x mu of x y is equal to f of x times mu of x. Okay. Now, what this leads to, believe it or not, okay, what we're going to do is recast this. Now, that's what multiplying by mu does, mu of x. Simple, just multiplying every entry on both sides by that. Now we're going to do something else here. Let's see what d by dx of, I'll get it the same order they do, mu of x times y. Okay, where mu is some function of x and y also is a function of x. They don't say it here, but it is. Okay. If you're doing a derivative, that's a product rule, right? Good old favorite product rule. And that would be mu of x dy dx plus y. Let me change the order. I think I want to change the order. Right now I want to change the order. Mu prime of x y. Okay? That's just stating the product rule. Okay? Now, notice that this is that term right there. Okay? That's this term here. So we could take this and subtract that term from this term. Okay? Sure that's what we want to do, but we could do that. All right. Okay. All right. We'll make sure that one thing doesn't look the same. That's what I'm debating. Maybe I ought to do this. Make this d mu dx, because they do it in the book. I don't think it matters. It just was easier to write the other. D mu dx times y. Okay.
See, I find that to be a little more confusing.
What's that?
By putting that dy dx there, I find it to be a little bit more confusing because
Yeah, it's a d mu dx, not dy dx. But they do it, and that's what they get. Okay. Now, and again, this is exactly this form here. Okay? All right. And if you say, since this form is the same, let's write it down again. Mu of x dy dx. Okay. If you want this to be the same as this, then you want this thing, d mu dx, this to equal p of x times mu of x, because that's what is multiplied by y. So you want this to be true. Okay? If that's true, then let's make that the perfect derivative. If it's true. Okay? That's what we want. We're leaving off the right-hand side altogether. We'll worry about that later. Okay? We were trying to get this to look that way. So if we can pick a mu, because we get to fuse the mu, right? Pick a mu so that this derivative is equal to this thing right here. It times whatever the function p of x, which we know that was given to us. So this is what we want to be true, that d mu dx is equal to mu times p. They left off the of x's there. It just makes it easier to see. The mu dp is equal to p times mu. Okay. Now, that we can solve by separating variables, by multiplying, so to speak, both sides by x. So we get d mu over, over mu is equal to p of x dx. Okay? Now, this is what we want to be true. We get to pick our mu, and we want it to be true that this thing is equal to that, so that this looks just like that then. Okay? So, this is separable, and we do separate it, and do this. Now, this is going to be log mu. Okay? And we integrate both sides. What's that? Okay. Integrate both sides, and you get log of mu is equal to the integral of p of x dx. All right? Now, how do we undo a log? What's the inverse function of it? E, exactly. If we did the e of this and the e of that, then this would give us mu. Because e undoes log, log undoes e, right? There's our mu of x. Is equal to e to the integral of p of x dx. Okay. Now, remember, where we started, we have that. We know what p of x is. And if p of x is integrable, then take a derivative, integrate. Don't worry with the plus c, just integrate the p of x. Whatever you get as the integral of that p of x, that is the argument for an e. Raise e to that value. That becomes your mu. Take that and multiply it by everything on the left, middle, and end. And you're ready to solve your problem. Okay? Now,
what about saying that the hard way, didn't they?
What's that?
They went about saying that.
Yeah.
The hard way.
Yeah, it's here. Finally, in equation 3, they say that. And there it is. Okay. Now, that's called your integrating factor. So we multiply that thing, that mu, by every term on both sides. And what always winds up is that then the left-hand side becomes a perfect derivative. This mu that you just figured, when you multiply that, that becomes a perfect derivative, okay? And all you have to do is integrate that with respect to dx. And when you do that, that's when you introduce your c. So don't try to memorize the formula. They write it down in ugly, gory detail and then say don't memorize it. And don't. It's not worth it, okay? So let's go back. I'm going to erase these, what I've written here, and here are the things. Put the linear equation in standard form. dy dx plus some p of x, y, is equal to some f of x. Whatever form it's given that you can't separate. If you can separate it, okay? But if you can't, then write it in this form. Whatever your coefficient is of dy dx, divide by it. You know, make that just that. So come up with that. There's your first step, okay? Then take this p of x, integrate it. Integral of p of x dx, okay? And once you got that integral, that's going to be some function of x. It's not going to have an integral sign anymore. It'll be some function of x, okay? And then raise that function e to the whatever this is, integral of p of x dx. It won't be that messy looking. It'll be something much simpler, okay? All right. Now, don't worry with the constant on that either, okay? Take that thing. This is now what we were calling the mu, and multiply it by both sides of your equation. So that'll be mu, I'm just going to say y prime plus mu p of x y is equal to mu times f of x. Okay? Now
what do you call the y prime?
That's your dy dx.
Okay.
Yeah. I just didn't, I was tired of writing it.
I got that.
Yeah, right. Okay. So, now, believe it or not, this right here is d by dx, if I could write it, okay, of mu times y. Okay? That's what it is. Now let's see if indeed that's true. Okay. It would be the first times the derivative of the second, right? Plus the second, which is y prime, your dy dx, but that is goodness gracious. Let me clean that up a little bit. Ooh, that's ugly. Okay. 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 No, I'm sorry. I didn't quite get that right. This is the integral e to the yuck. Let me start this one over. Okay. D by dx of oh yeah, I did have it right. This is mu times y, okay, because remember mu is this thing, okay, but it's much easier to just call it mu, it's a lot shorter, times y prime plus, And then derivative of mu, okay, derivative of mu will be this thing right here. Okay. All right. Let's do this again. Mu of x is equal to e to the integral of p of x dx. Okay? So if you do d mu dx, the integral of that, that's equal to e to the integral of p of x dx. All right, remember? E times the derivative, chain rule. Okay, your favorite, chain rule, right? Derivative of an exponential function is that same exponential function times, and the chain rule is the derivative of this, right? Okay. Now the derivative of this, the derivative of an integral is p of x. You know, a derivative undoes an integral, and an integral undoes a derivative. So it's going to be e to the x dx times p of x. Well, guess what? And then that's times y. Okay? So this thing right here is this. It's mu is this. This is mu. I can't write. Okay? Times p of x. Okay? That is derivative of mu times y. And there's the y. So that always works out that way. Now, don't try to memorize this. And this is equal to mu times f of x. Okay? Mu is just a function, you know, of x. Okay? Now, so what you do now is now you can separate variables. D of mu y is equal to the integral of mu f of x dx. Okay? Now,
Why did you put an interval in there?
what's that? Yeah, okay. Okay, I'm sorry. Wait, I should have left this off. Okay. What we're doing is integrating both sides. Okay? We integrate this and we integrate this. Okay, well, we multiply by dx. Okay, or so to speak, right?
Okay.
Now, the integral of a perfect derivative is uy. Mu y. No, that's not u. Mu y. So this product is that. Okay? All right? And then divide both sides by mu. And you've got y is equal to that. Now, again, don't try to memorize. Oh, and here's where you put your plus c. Okay? You need a plus c in there somewhere. You wait until the end and put it in. Okay? Now, again, they say don't memorize this. Now, they actually have some more mess there. Don't memorize it. So, all right. So let me go back. I was writing these things out. So let me go back and do these again. All right. It was based on this, but I'd already done all that, or most of that before. Okay, all right. So first write the form in this way, okay, standard form. Then do your, here's your p, some function of x, do the integral of p of x dx. That's what you do next. Just take the derivative, integrate the p of x. Then raise that, have that be the power of e. Okay? And that then becomes your mu.
You have the test for the differential equations.
Yeah, I didn't give it to you? Okay.
No, I can't. I only got the linear.
Right. Yeah. Here it is. That's it. Okay. Okay.
I don't know if you were aware. I know you had an
Is it time?
You have another class you gotta go to. but
Yeah.
it's
Is it time?
it's 10.
All right, glad you said it. Okay, thank you. All right, we'll pick up there next time. We'll go back over that. That's a good place to start next time to do the rest of it. All right, so I guess, because he did stick his face in the door, I'll put, Justin was here today, but everybody else was not. We've lost Jordan. I got him for 3 classes, and it's been, wow, quite a while since he's been in this one. So I hope he shows up. I shouldn't be saying this on